Continuing on physical chemistry, chapter 6, we're beginning section 3 right now. So now we're going to talk more about the temperature dependence of the equilibrium constant Kp0, which we defined in the previous section. So Kp0, remember, we said is a function of temperature, at least for an ideal gas. See handout figure 24. So the change in the Gibbs free energy at the standard state is equal to minus RT times the natural log of Kp0. So solving for natural log of Kp0, we get minus delta G0 over RT. Now what we want to do is take the derivative with respect to temperature. So we get the derivative with respect to temperature, the natural log of Kp0, equals the derivative with respect to temperature of minus delta G over RT. Now since delta G is temperature dependent, we have to use the chain rule when finding the derivative here. So we have the derivative with respect to temperature of the natural log of Kp0 is equal to delta G0 over RT squared minus 1 over RT times the derivative with respect to T of delta G0. So now I'm going to say, okay, the derivative with respect to temperature of delta G0 is the derivative with respect to temperature of the sum over I of nu I, the molar Gibbs free energy in the standard state of substance I, which is going to be equal to the sum over substance I of nu I times the differential of the molar Gibbs free energy of substance I with respect to temperature. Now remember, the differential of the molar Gibbs energy is equal to minus the molar entropy times the differential of temperature plus the molar volume times the differential of pressure. Now if we have a constant pressure process, we'll say dP is equal to 0. So then we just have molar, the differential of molar Gibbs energy is equal to minus the molar entropy times the differential of temperature. So that gives us, well, what we have here. Differential of molar Gibbs energy is equal to minus molar entropy times the differential of temperature. So just divide by dt to get it over there. We have the differential Gibbs free energy, molar Gibbs energy divided by differential of temperature minus is equal to minus the molar entropy. So if we have a finite change, we'll say that the differential of the change in the molar Gibbs energy in the standard state with respect to temperature is equal to minus the molar Gibbs entropy in the standard state. So now we have the differential of the natural log of Kp0 with respect to temperature is equal to delta G0 divided by RT squared plus 1 over RT times the change in the S0. Should that be molar? No, not molar, because this isn't molar. So this is all extensive here. At least that's what it shows here. Okay. So we have the derivative of natural log of Kp0 with respect to temperature is equal to delta G plus T delta S over RT squared. See how we did common denominator there. And so delta G plus T delta S, that's going to be the change in enthalpy, standard change in enthalpy over RT squared. So that gives us the derivative of the natural log of Kp0 with respect to temperature is equal to the standard enthalpy change over RT squared. This is called the Van Hoff equation. This is the differential form of the Van Hoff equation. So remember, it's understood that this enthalpy is only specific change in heat, standard change in heat, standard change in enthalpy, that's temperature specific. It's at a certain temperature. So Kp0 depends on the change in the enthalpy at the standard state. So let's integrate that. So we're going to have the differential. Well, first we're going to move dt over here so we have like variables. So we have the differential in the natural log of Kp0 is equal to the standard heat over RT squared dt. So integrating, we're going to go integrate from Kp0 T1 at temperature 1 to Kp0 at temperature 2 of the differential of the natural log of Kp0. That's going to be equal to the definite integral from temperature 1 to temperature 2 of the standard enthalpy of formation divided by RT squared with respect to temperature. Now let's just assume for a bit that the enthalpy in standard enthalpy change is not temperature dependent. Then we're going to end up with the natural log of Kp naught at temperature 2 divided by Kp naught at temperature 1 is roughly equal to, because we assumed that it's constant, the enthalpy of formation in the standard state divided by R. R is constant, so you can pull that out. The integral from T1 to T2 of 1 over T squared dt. So that's going to be delta H naught over R times 1 over T1 minus 1 over T2. Now the natural log of Kp naught at temperature 2, natural log of Kp naught at temperature 1 then, is going to be roughly equal to a change in enthalpy, oops, actually there should be a naught here, over R times 1 over T1 minus 1 over T2. This is the integrated form of the Van Hoff equation. Might want to emphasize this version. So that's the integrated form of the Van Hoff equation. And of course R is just the gas constant, 8.314 joules per mole Kelvin. Now the derivative of 1 over T with respect to T is equal to minus 1 over T squared. So we can actually rearrange that a bit and say, okay, the differential of 1 over T is equal to minus 1 over T squared times the differential of T. See, all we did was we take this and we multiply by dt. So solving for dt, that'll give us dt is equal to minus T squared times the differential of 1 over T. So we're going to substitute that back into the Van Hoff equation. Let's see, the differential form of the equation. That's going to give us the derivative of the natural log of Kp naught over minus T squared divided by the differential of 1 over T, and that's equal to delta H naught over RT squared. Or to put another way, the derivative of the natural log of Kp naught with respect to 1 over T is equal to, see how these T squareds cancel it out. So we get minus delta H over R. So what we can do is plot the natural log of Kp naught divided by 1 over T. So here's our vertical axis, natural log of Kp naught. Here's 1 over T. So if you have an exothermic reaction, delta H is less than 0. If you have an endothermic reaction, delta H is greater than 0. Now, if the change in enthalpy doesn't depend on T, then these curves will be straight lines, because the slope of those is minus delta H naught over R. So the slope is going to be negative. Let's see if I can show that. The slope is going to be negative if it's endothermic. Slope is going to be positive if it's exothermic. Now, if the graph isn't straight, then that tells you that your change in enthalpy is not constant with temperature. It's temperature dependent. Now, we showed before that the change in the standard change in Gibbs free energy in standard state is roughly equal to the change in the enthalpy in the standard state when you're at very low temperature. But the change in the Gibbs free energy in the standard state is roughly equal to, these should probably both be roughly equal to, their estimates, minus RT natural log of Kp naught at high temperature. Okay, but also delta G naught is equal to minus T delta S naught at very high temperature. So setting these two equal to each other, obviously we're assuming at high temperature now, we get T delta S naught is equal to RT natural log of Kp naught. Now, we already showed before, minus RT natural log of Kp naught is equal to delta H at low temperature. So using those other two relations for low temperature, we get the natural log of Kp naught is equal to minus delta H over RT when you're at low temperature. And then, of course, delta S naught is equal to R times the natural log of Kp naught at high temperature. That's it for section 3.